Hello. In this video, we will study properties of homomorphisms whose domains are cyclic groups in order to eventually give a classification of cyclic groups. So we begin with a proposition that has actually nothing to do with cyclic groups and works for arbitrary groups. And it tells us something about the orders of elements in a group. So let G be a group, and we take a little x to be an element of G. And suppose that we have that x to the n is the identity, but also x to the m is the identity. Then the conclusion is that if I raise x to the greatest common divisor of m and n, I also get the identity. And as actually a corollary to the first statement, we're going to prove that that means that if x to the m is equal to the identity, then the order of x divides m. Now, so far we know sort of a weaker statement to the second one, namely, remember that the order is the smallest positive power that gives you the identity. Which means if x to the m is equal to the identity, that means the order is less than or equal to m. Okay, but this time we'll get a more refined information. We're gonna get that the order of x divides m. So if, for example, we find out that x to the 18 is the identity, then we get possible orders for x from just that information. The possible orders are the divisors of 18. So in particular, 5 cannot be the order of x. It must be the divisors of 18. So 18 or 9 or 6, 2, 3, or 1. Okay, so let's prove this proposition. So we know by the fundamental theorem of arithmetic, we get that there exist R and S in Z such that the GCD of M and N, so D, is equal to Rn plus S M. So if I raise x to the d, that's x to the Rn plus Sm, but that's the same as x to the n to the power R, x to the m to the power s. And what I know is that x to the n is the identity, so that's the identity. And so is this. So I get that this is the identity to the R times the identity to the S, so the identity. Okay, so this proves the first part. This proves the first part. What about the second part? So if x to the m is the identity, let's write down, let n be the order of x. So if, look, m does not have to be a positive integer, right? M is just any integer. So if m is 0, anything to the 0 is the identity. Well, but then, clearly, the order of x divides m, because every integer divides 0. Every non-zero integer divides 0. The order of x is a non-zero integer, so if m is 0, then we get that claim. So let's now assume that m isn't 0. So now assume m isn't 0. So since some non-zero power of x equals the identity, namely x to the m, x to the m is the identity, right? X to the m is the identity, and m is non-zero, so some non-zero power of x is equal to the identity. We get that the order of x is finite. Now, why is that true? Well, if m is positive, then because x to a positive power is equal to the identity, I know then the order is at most m. But what if m is negative? That doesn't give me any positive integer such that x to that positive integer is the identity. Well, actually it does, because if x to a negative integer is the identity, then x to the negative of that negative integer would be the identity. Right, so note, if x to the m is equal to the identity for a negative m, then x to negative m, and this is now positive, this thing is now positive, is equal to x to the m inverse, which is the identity inverse, so it's the identity. So even if m is negative, there is still a positive power of x that gives you the identity, which means the order of x is less than infinity. Okay, so now let's let D be the GCD of m and n, where n is when n is the order. So surely x to the order is the identity, and we also know x to the m is the identity. So by the previous part, we get x to the d is also the identity. So by part 1, we get that x to the d is the identity. But what do we know about GCD of two numbers? One of them is being positive. The GCD is always less than or equal than the minimum of the absolute values of these numbers. So we get surely that the D is between 1 and n. Right, the GCD of two non-zero numbers is, even if one of them is negative, is always less than or equal than the absolute value of either of these numbers. So n is positive, so that means d is less than or equal than n, and of course it's greater than or equal than 1. But then, so d must be equal to n by the minimality of n. Remember, the order of an element is the smallest positive integer, such that x raised to that integer gives you the identity. Because d is a positive integer, which is less than or equal than n, and I know x to the d is the identity, and n is the smallest such, I must get that d must equal to n. So what do we get? So what does it tell me? That tells me that n is equal to the GCD of m and n. N is the greatest common divisor between n and m. In particular, n is a divisor of m. Hence, n must divide m. It's the greatest common divisor between m and n, so in particular it must divide m. And this is what we wanted to prove, right? The order of x is equal to n, and it divides m. So we're done with this proposition. Okay, we're going to use this proposition very soon. Let's take a little break so I can find the eraser.